right, shall we start again? So in the remaining time, what I will try to do is to get to the time-dependent Hartree-Fock equation. And that will probably be all what we were going to do for today. Okay, so what we showed is that, a bit quickly, is that a variational principle on the action. So you have the Dirac action, and you require the action to be, this action to be stationary. You recover the Schrodinger equation. To do that, you can assume any restriction on the variational space of the state. So the state can be whatever it wants in Hn, in the Hilbert space of n particles. So it could be correlated as well. You see, it doesn't have to be, it can be any state, so it can be independent particle state or correlated state. Now but we know we can't solve the Schrodinger equation exactly. So the idea behind variational principles, what makes them useful is when you restrict the variational space. Instead of considering any variation in Hn, in the full Hilbert space, you just take a subspace, something which will be easy enough for you to compute in a numerical code or whatever, and then you solve the variational space in this subspace. So if you want, if that's Hn, and you allow your state to be whatever it wants in this state, in this space, you recover Schrodinger equation. The variational principle gives you Schrodinger. Now the idea is to usually get a subspace which is smaller and which is easy enough so you can actually solve the problem numerically or whatever. Okay? So that's the idea. Now, so that's how we will get the time-dependent Hartree-Fock theory. There is many ways to get this theory, this approach, this equation. But we will use this approach, which is to start from the Dirac action. And to require this to be 0. But we will do that in a subspace F. The advantage is because you require a variational principle, you will have, if you want, the best approximation of the exact dynamic within this subspace. So if you are doing a good job, the job of the physicist is to find what is the good space to use, which is simple enough so that you can solve the equation on a computer, and which is incorporates enough complexity so it can give a good approximation to the dynamics you are looking at. So that's the only thing physicists have to do, is to find the right space. So in order to get TDHF, the idea is to restrict the space to Slater determinants. So independent particles at every time. The reason, so we know it's going to be an easy thing to solve, because that means that if the state at any time is restricted to be a Slater determinant is the simplest state I can imagine of. Okay, it's independent particles. If I restrict my state to be a Slater determinant at any time, then I know I will be easily able to put that in a computer. That's relatively, that's not very complicated. While if I was solving the state in the full space, I will have very quickly too many Slater determinants to take into account. So I'm just taking a restriction of the full space to the space of single Slater determinants. Now, is it going to work? Usually, well, at least the variational principle will tell you it's the best thing I can do within this space. Is it good enough? Then you need to solve and compare with experiment, and if it's working or not. That's often what theorists have to do. So let's do it. We'll solve this variational principle, but restricting psi to be Slaters. Okay, so what is different now? The Slater is something I can write. If I force my state to be Slater at any time, that means that at any time I can write it, as I did before, as a product of state of all the occupied single particle states. And because my particles are fermions and they are identical particles, I should have something which is antisymmetrized. So let's write this antisymmetrization operator. So that's just an independent particle, product of single particles, and I antisymmetrize everything. That will give me a Slater. So if you want, that's the form of the trial state, so the state which will explore this subspace F here. Okay? It's the most general Slater form I can think of. So now you need to do it. So what you have an Hamiltonian, you have a time derivative. So let's look at the time derivative first. So you see you have a product of n functions of time. And you are looking at the time derivative of that. The antisymmetrization operation doesn't depend on time. And what you have is, so you will have the time derivative, you have the product rule, so you have the time derivative of the first you have the time derivative of the first state times everything else, plus the time derivative of the second state times everything else, and so on and so forth. So you have a sum from I equal 1 to n, a or n, doesn't matter, of phi 1 of t. Then the time derivative of phi I of t, and then phi n of t. Okay, so you just have a sum because you are acting your time derivative on each single particle state. So nothing really complicated here. And you see that you have the time derivative, but you have the overlap with the bra to take into account. So you have to calculate that. So that will be just the overlap of the bra on that. Time A and what I've put here. I'm too lazy to rewrite it again. So essentially you're just calculating the overlap of the Slater as a bra times the Slater as a ket with the time derivative acting on it. So The thing is relatively simple when you get that. Every state, you see, which is not on which you do not have the time derivative, can only overlap with the same state. If you want to have a phi 1 here, its overlap with phi 1 is going to give you 1. But its overlap with any other state is going to give you 0. So at the end, this is just a sum over I equal 1 to n of phi I of t d on dt phi I on t. Now I went very fast here. So I'm sure you need a bit of thinking to see that you can actually go from this complicated expression with a many-body Slater as a bra and a many-body Slater on the left to this simple expression where you just sum overlaps of single particles. So instead of doing it properly, rigorously, what I will do now is to show how it works with just two particles. And usually if you believe it works with two particles, you can generalize it for many particles. Is that okay? It's an you will see, it's an anti-symmetrization. So essentially if I don't have that, this is just like an independent many-body state of distinguishable particles. Because they are all identical, I need this anti-symmetrization operator. So let's do it just for two particles. Maybe that will be a nice example. So you have phi 1, phi 2. You have a like here. So that's your state on the left. You have the time derivative, and you have a state on the right, which is a phi 1, phi 2. Now we already saw that the action of this anti-symmetrization operator is to give me 1 over square root of 2 phi 1 phi 2 minus phi 2 phi 1. Okay, so that's what we did at the very beginning. That's just an anti-symmetrized state of two particles. My particle 1 in phi 1, my particle 2 in phi 2, minus the permutation, particle 1 in phi 2, particle 2 in phi 1. You have the same thing on the left. Now I'm sure I'm going to do something wrong with the sign, but I think it's good, it's done properly in the notes. And I should have the time derivative here. Okay, so you just have to calculate the overlap of this with this, and there is a time derivative acting on the right. So let's just act the time derivative on this first. So we have 1 over square root of 2 d on dt of phi 1 phi 2 plus the time derivative on the second state and minus the cross term d on dt of phi 2 times phi 1 minus phi 2, sorry, d on dt of phi 1. Now when you overlap with that, you see you have to overlap the first particle with the first particle. So you have the phi 1 d on dt phi 1, it's fine. Phi 2, that's just going to be 1. The overlap of the single particle state is 1. And for this one, however, phi 2 d on dt phi 1 and phi 1 phi 2 is going to be 0. Phi 1 and phi 2 are orthogonal. Two particles can't be in the same state. They are fermions. So when you take that into account, you end up with something much simpler. This is stop the recording. So what you have is 1 square root on 2, 1 square root on 2, it's just 1/2. And you will have phi 1 d on dt phi 1 times 2 phi 2 is just 1. Let's do this one times this one. So phi 1 it's just 1. We have phi 2 d on dt phi 2. So plus phi 2 d on dt phi 2. Now let's look at the other term. We have this, this times this is going to be 0 because I have a phi 2, phi 1. They are orthogonal, so that's 0. And this times this is going to be 0 as well. Phi 1, phi 2 is going to be 0. So now I still have this times this. Well, that's 0. Phi 1, phi 2 is 0. Phi 2, phi 1 is 0. So I'm just left with this times this. The minus times the minus give me a plus. So I don't do anything wrong with my signs. And I have phi 2 d on dt phi 2. I'll do things in detail only once. Next time, we will just do it much faster. And the last term, phi 2 is 1, phi 1 d on dt phi 1. This is just equal to phi 1 d on dt phi 1 plus phi 2 d on dt phi 2. So that's what I told you for a many-body state. What I wrote here. And I just did it in detail for a two-particle state. And indeed, you see that it's a sum of phi d on dt phi for each particle, each occupied state. So if you now you believe me, it's working for two particles, so you believe it's working for as many particles as you want. Okay, so we have done only one term. We have done the time derivative term. We still need to play with the Hamiltonian term. So remember the action. I should clean some of this board. So the action is time integral t0 t1 dt of phi I h bar d on dt minus h phi. So we have done this term, phi dt phi. We have just shown that it was the sum over each single particle overlap of d on dt. Now we have the Hamiltonian. And that's where things are getting very simple, because I told you I assume we know what is the nuclear interaction, which is equivalent to say I assume we know what is the energy density functional, which is another way to write how the system interact with each other, how the particles interact with each other. So we are going to call this object phi h phi, where phi is a Slater. We are going to call that an energy density functional. So that's what, if you want, that's what the people who are working on the interaction are going to give me. They're going to give me this object, and they are not going to give it as a form of a Hamiltonian. They are going to give it as a functional of the one-body density rho. And that's completely equivalent if phi is a Slater. So let me tell you a bit more what is this rho, and then we will see, we will get to the TDHF equation. Who have heard, I'm not going to play the game of raise your hand again, but I believe you have all heard of what is an energy density functional. If not, it's really simple. It's just, it's by analogy with what we call density functional theory in condensed matter, where instead of looking at summing the interaction between each pair of particles, we just take the total density of the system and we look at how the energy change when I change this density. Now there is a bunch of theorem behind it which says that you can have a one-to-one mapping between an energy density and I'm not going to go into that. That's a job of people who are working on the interactions. But essentially, the modern version of nuclear physics is always using what we call energy density functionals and not really Hamiltonians, unless you are starting from ab initio formalism. But most people who are looking at many-body problem for, I don't know, collision of particles is always with energy density functionals like that. So, rho here is what we call a one-body density matrix. So it's a matrix, and its matrix element, rho alpha beta, will be the expectation value on the Slater psi. Phi. I mean, it doesn't have to be a Slater, but in our case, it is a Slater, of A dagger beta, A alpha. So that's the matrix element of the one-body density matrix. So essentially, if phi is a Slater, you see you're killing one of the particle, you're creating another one, and then you overlap with what you had at the beginning. If phi is a Slater, it's very straightforward, because you can only kill a particle which is already here. And this is also killing a particle on the left. So you can create a particle on the right or kill a particle on the left. And if you don't kill the same one, it's going to be 0 at the end. You are going to have an overlap of single states which are not the same. So you need to kill the same on the right and the same as on the left. So alpha should be equal to beta and should correspond to an occupied state. So that's a very simple object in the case of a Slater. So essentially that will be we have the antisymmetrized thing. I will be, it's on the note, I will be quick on that, but you get the idea that this is essentially, this has to kill the same particle on the left and on the right, so that gives the same, that just gives the occupation number of the state alpha. So it's only, n can be 0 or 1. 1 if it is an occupied state, 0 if it is not an occupied state, and it has to be the same on the left and on the right. So it's a relatively simple object at the end. Okay, let's go to, let's now use the, let's derive the TDHF equation. So we have now both terms. We have the term for the time derivative and the term for the Hamiltonian. And as before, we need to look at phi and the bra and the ket as independent variables. We were only going to do it for the variation according to the bra, okay, and the variation according to the ket is the same technique as what we did just before for the exact Schrodinger case. And more precisely, this is actually a Slater, so that's a product of n single particle state. So we have n variables for each of the occupied particles. With an anti-symmetrization somewhere. Okay? So we need to do the variation for each of the single particle because we have n particles. All right, let's then calculate the variation of S according to phi. So these ones are going to be phi star I of X. What I mean by X here is any single particle basis. It could be the position, spin, and isospin, or it could be harmonic oscillator state, whatever. It's just a generic notation, so it could be, for instance, position, spin, and isospin of the single particle. So let's calculate that and force it to be 0. So for the first term here, we have integral T0, T1, dt of the delta on delta phi I star of X and T. I should have time as well. And that's T dash. And show that it was just the sum of I equal 1 to n. And I should just use a different letter. If this is a I, this should be a j. Can't use the same one. And we have phi j d on dt phi j. But that's just the integral over dy of phi y star of j at the time t dash. Sorry, I'm getting tired. Y t dash d on dt phi I j, going to do it, of y and t dash. Okay, I just expressed this in one single particle basis and use the closure relationship. So then you do the derivative of this term. Of course, it's going to be non-zero only if I is equal to j. So that's going to give you a delta ij. It's going to be non-zero only if x is equal to y. So you are going to have a delta x going to be non-zero if t is equal to t dash. So everything is going to be has to be equal at the end. So that's for the first term, and the other term is just minus delta on delta phi I star x t of E of rho. So noting that delta of phi star j y t dash with respect to phi I star x t is just delta ij, delta x minus y, and delta t minus t dash. You kill all the sum, you kill the integral, you kill this sum, and you kill this integral. So you just have, and there should be an IH bar in front here. IH bar d on dt. So you have IH bar d on dt of phi j of x and t. So that's for the first term. It looks familiar. It looks like Schrodinger. And now we have to do the variation of the energy density functional. It's a bit tricky, but let's do it. So my rho is actually a one-body density matrix, and its matrix element rho alpha beta, as I said before, is just the expectation value of A dagger beta, A alpha. Now I need to write that a bit differently so I could see the phi star appearing in order to do the derivative of it. So these phi's here are just product of phi 1 phi j, and same thing here, phi 1 phi j with an anti-symmetrization. So essentially all the creator and annihilator have to act on the same particle, and all the other particles are going to give an overlap 1. So this is going to be the sum over I equal 1 to A of phi 1, etc. Phi I A dagger beta A alpha. Now, if you are a very rigorous physicist, familiar with second quantization, first quantization, and so on, what I'm doing here is not very rigorous because I'm mixing both notations. So just close your eyes. That's just to and I will just erase it in a minute. Phi n. So you see that first the creation, that's just to show that the creation and annihilation has to be on the same state. Now essentially what this means, what I just wrote, what this means is that you're going to calculate the overlap of phi I with the state alpha and phi I with the state beta here. Does that make sense? That's just a proper first quantization notation of what I just did before. Now all these things are just one. This is one, and so on. So I just have a sum over phi I beta, the overlap between phi I and beta, and the overlap between alpha and phi I. I'm almost there. So now I want to write, I see my phi I appearing, so I want to write them as a function of x. So I just need to choose a basis x, which for instance is position, spin, and isospin. So let's do it. My rho alpha beta, or let's call it x and x dash, is just the sum. So I just replace alpha and beta by x and x dash. It's just choice of a different notation if you want. So I have a sum from I equal 1 to a of phi I star x dash. Yes, phi I x. Okay, I just did exactly the same thing, but instead of alpha and beta, I use x and x dash. And then that gives me my phi and phi star. Okay, so I know how to express rho as function of phi and phi dash, and phi and phi star. What I want is to do the functional derivative of E of rho. So what I will do is first to do the derivative of E according to rho, and then the derivative of rho according to phi. So delta E of rho with respect to delta phi I star of x. Now that's when I need to wake up. So that's going to be delta E of rho with respect to delta rho of y dash, delta rho of y dash with respect to delta phi I star of x. And of course, what did I forget? You see on the left I have no y dash. And on the right I have a y and a y dash. I need to sum over all the possible variation according to y and a y dash. So I should have a sum here. If you are not familiar with functional derivatives, that may be a bit tricky, but that's essentially an extension of derivation, but when instead of deriving according to a variable, you derive according to a function. So you should see all these row of y dash as one possible variable. So each row of something is one variable. So you have an infinite number of variables. So when you do a derivation, you need to sum over all the possible variables. Almost there. Promise. This is, now to calculate that, I just need to use this expression. Now that's straightforward because I see that I have expressed rho as function of phi star. So the derivation according to phi star is going to just give me phi I of x. Yes, the delta, but because I use I on both sides, it is. Now this, I'm not going to do anything with it because I haven't given you an expression for E of rho. Again, that's the job of people who are working on functional energy density functionals or the interaction, and they give you that. So you can use, for instance, Kerm functional, Goni functional, Fayence functional. There is plenty of different functional on the market, which will be a function of rho and its derivatives and its spin dependence and isospin dependence and so on and so forth. And from that, you can calculate the functional derivative. Now, what we're going to call that is h of y dash and y. This functional derivative of E with respect to the density is just a small h. And at the end, that's a Hartree-Fock Hamiltonian, which will be a mean field Hamiltonian. So let's wrap up all the terms together. Hoping I didn't do too much mistake when I wrote that. Yes? So, yeah, in principle, delta x minus y or y prime, like that. Should be correct in the notes. Okay. So let's wrap that together. I erased the wrong things. So we ended up with I h bar d on dt phi I of x and t. Okay. Minus, now we have integral dy dash, but there is a delta function, so we just have one integral dy of h of x, y, and phi I of, and that should be of y, sorry, phi I of y, and that should be equal to 0, or equivalently this should be equal to that. So what is that? How would you call this equation if I started writing that, just that? It's a Schrodinger equation. In fact, it's not really, it's a nonlinear Schrodinger equation. It's nonlinear because h depends on rho. See? When you have this object here, it depends on rho. So it depends on the solution, it depends on the state of the system. So you have a Hamiltonian which acts on a particle, on the wave function, but at the same time depends on the wave function itself. So we call that self-consistent Hamiltonian. It depends on the state of the system on which it is acting on. So it's a nonlinear Schrodinger equation. It's not exactly the usual Schrodinger equation, which is purely just linear. So H here is called the single particle Hartree-Fock Hamiltonian. So how many, I just wrote one equation, but how many do we have? n. We have one equation per occupied single particle. Okay, so we have in principle I range from 1 to A. And you can always write that in a different form. So now you have written it as function of functions, so wave function and matrix element of H. You can write it in a matrix form. For instance, I H bar d on dt of phi I H phi I. So that will be where phi is a vector and H is a matrix. So that's how you will encode things in a computer, for instance. You will have just product of matrix time vectors. And you can even put things a bit more abstract by writing that in the Hilbert space. So quick question, H belongs to which Hilbert space? H1, Hn? It belongs to H1 because it's acting on a single particle. However, it's a function of the density which is calculated from all the wave functions. Okay. Come on. We should probably stop here, I guess. So tomorrow, what I will start from that. So we have done a relatively cumbersome part, to do all this derivation and notation and so on. We end up with TDHF equations. I'll just write them in a different form tomorrow, what we call the Liouville form, and then I'll show you how we solve it in an algorithm in a computer. How do you actually solve the TDHF equation? What will be the form of the algorithm? It's just relatively simple. And then we will start and then we will see how far we go. Thank you.